Good morning, students. Today's topic diffusion capacitance. In last class, we discussed the transition capacitance. Transition capacitance is worked under reverse bias condition. That is another name is transition capacitance is space charge capacitance. Diffusion capacitance is a worked under forward bias condition. The capacitance is carries into existence. That is called a diffusion capacitance. The diffusion capacitance is also called as storage capacitance. Storage capacitance. Now consider a p-n junction diode. This is a p region, this is a n region. In p region, the majority carriers are holes. In n region, the majority carriers are electrons. In the p region, the minority carriers are electrons. In n region, minority carriers are holes. This is the junction. This is the p-n junction without unbiased condition. This is diffusion capacitance is worked under forward bias condition. We can apply to the forward bias to the p-n junction diode. This is a positive, negative. This is a forward bias voltage Vf. Then forward bias voltage is applied to the p-n junction diode. This the p region is connected to the positive terminal. N region is connected to the negative terminal. In positive, negative means this is repelled. Then the junction width, the width of the depletion region will be decreases. Decreases means narrow depletion region. Narrow depletion region. Then the forward bias condition we are applied. The diffusion process starts. The diffusion process starts in p-type region. The majority carriers of holes is diffused and cross the junction that will be moved to p region to n region. Similarly, in n-type, majority carriers are electrons that will be diffused, that will be cross the junction. In electrons will be cross the n-type to p-type. Then this is a p-type, n-type. This is a junction. This is the width of the depletion region W. We are applying forward voltage Vf, positive, negative. The diffusion process in p-type, we are applying in p-type diffused. We cross the junction. Near the junction in n-type region, the positive charge carriers, positive concentration of charge carriers, immobile ions will be formed near the junction. Similarly, n-type region, majority carriers are electrons that will be diffused to cross the junction. In p region, near the junction, negative charge carriers, the immobile ions, the carrier concentration of immobile ions will be formed. We can apply the more voltage, forward voltage to the p-n junction diode. The many number of negative immobile ions will be formed near the junction in p-type region. Similarly, the many positive charge immobile charge carriers are formed in n region near the junction. See here, this will be act like a capacitors. This will be act like a capacitors in plates, like plates. This is act a plate 1. N region is act like a plate 2. See, this is a one plate. In this near the plate, the positive charge carriers, and another plate near the junction, the negative immobile charge, negative charge carriers. This is will be similarly like as a capacitors. This is a diffusion capacitance. The two plates are acting as a diffusion capacitance. Next one is you can increase the charge carriers. We can increase the forward voltage. We can increase the forward voltage. Increases. Then concentration of charge carriers are increases. That is nothing but change in charge by change in voltage. Change in charge by change in voltage is nothing but a diffusion capacitance. We know the current formula I equal to Q by tau. What is the Q? Is a charge. What is a tau? Mean lifetime charge carriers. Mean lifetime charge carriers. Next, we can calculate the charge equal to tau into I. Tau into I. You know the current formula I equal to I naught into e power v by eta Vt minus 1. This equation is substituted in charge Q equal to tau I. This is the equation number 1. This is the equation number 2. Substitute equation 1 in equation 2. Is a Q equal to tau into I is nothing but I naught e power v by eta Vt minus 1. This is the equation number 3. Again, differentiate equation 3 with respect to voltage. dq by dv equal to tau into I naught into e power v by eta Vt minus 1 into 1 by eta Vt. Okay. This equation. Before differentiation, the equation 3 e power v by eta Vt minus 1 in forward bias condition e power v by eta Vt is very much greater than 1. We can neglect the 1. Q equal to tau into I naught into e power v by eta Vt. Now we can differentiate with respect to voltage tau into I naught into e by eta Vt into 1 by eta Vt. You know the current formula I equal to I naught into e power v by eta Vt minus 1. In forward bias condition, e power v by eta Vt minus 1 is greater than 1. Is greater than 1. We can neglect the e power v by eta Vt is greater than 1. Then neglect the 1. Then I equal to I naught into e power v by eta Vt. Substitute this I value into before equation dq by dv equal to tau into I by eta Vt. Coming to the characteristics of diffusion capacitance. In y-axis is a diffusion capacitance, microfarads or nanofarads. In x-axis, forward voltage, the units are voltage. In 5, 10, 15, 20, like that. In this 10, 20, 30. We can increase the forward voltage, the corresponding diffusion capacitance is increases. In this previous equation, in dq by dv equal to tau I by eta Vt. You know the dq by dv is nothing but diffusion capacitance is tau I by eta Vt. This is nothing but diffusion capacitance is directly proportional to the current. We can increase the diffusion capacitance, the current will be automatically increases. Similarly, we can increase the forward voltage, the diffusion capacitance is accordingly increases. Finally, we can increase the forward voltage. The forward voltage increases, the charge will be increases. The charge is increases is nothing but current is increases. Finally, you know the equation, CD is directly proportional to current. The current will be increases, the diffusion capacitance increases. Thank you, students.